So he's going to talk to you about his work and what he's learned with his experience abroad. So,
thank you. So I'm just going to start by presenting the work that I've been doing before. So I started here in the spacecraft group during the master. And during the master, I've been working with a specific instrument, BERM, a detector in the space mission, and I've been working in the calibration and the characterization of the instrument. Now, during the PhD, I'm more focusing, trying to use the data from this instrument and other instruments to do some analysis with the data and to analyze some solar events that where I'm talking more today. Okay, but before talking about the solar events and the analysis of the events, I will talk a little bit about the mission that I'm working, so you get a little bit of an idea of other missions too that I will talk about later. The detector I've been working with, there is BERM and some other detectors, and before that, about also the radiation sources, so you can understand what I'm going to detect with the detector. And at the end, the analysis of the data, in this case with a specific event from the sun. So the mission is the BepiColombo mission. It's a mission to study Mercury. So today I'm talk about more solar events, but this mission is the main objective is to study the Mercury, the planet. So it is composed of two spacecrafts, one from ESA and one from JAXA, and it has several objectives like studying the surface of the planet, the interior of the planet, the evolution of the surface, and also the magnetosphere. But as I told. Okay, I think it's not sharing. Okay. Okay. Everyone can see online? Okay, I hope now everyone can see.
Este cabo é bem lixado. Não, é mesmo aí. Deixa eu funcionar isso. Isto foi a vida, é isso.
Está ligado diretamente ao projetor, não sei como é que está. Posso ver como é que está ligado?
Podes ver, mas eu acho que isto é... Se calhar é melhor. Não sei também.
Okay, so está aqui com um bocado de está aqui com um bocado de delay a avançar os slides. Que slide é que está aqui? Okay. Okay, so I was talking about the mission. So a mission to Mercury to study basically the planet. But as you can see here, it has a big timeline. So it was launched in 2018 and it's arriving to Mercury in 2026. And I've been focused more in what's happening in the middle between. So it's not the main stage of the mission, but during this part you can take a lot of data, especially from the sun, solar events, and also from Mercury, but I'm most focused on the sun. I will just point out this first flyby. So during this period, the mission is doing several flybys. This first one to Earth, it's an important period that I will mention later, but it's an important period basically because it's a well-known environment, so it will always be important to the mission and to the instruments. So now talking a little bit about the radiation sources that we will encounter during this mission. I will divide those in three groups. So the solar radiations, the sources that comes from the sun, what you can encounter around the Earth, and what comes from out of the Earth and the sun. So in this case, galactic cosmic rays. And we'll start by those. So as you probably know, galactic cosmic rays, mainly protons, very high energetic protons, and I'm saying very high energetic protons in relation to the energies I'm going to talk about next. So it starts more or less in 1 GeV. I will not talk about those kind of energies here. Going to the range of hundreds of MeV, it's the maximum energy that we'll talk about. So more or less constant fluxes, but affected by the solar cycle, and this can be important for the missions, and I will show you how this can affect what we detect, this solar modulation that you also can see here by the maximum and minimum fluxes. Okay, now the radiation sources that came from the sun. We first have this solar wind, so a continuous emission of plasma from the sun. This is what's always happening. It can have velocities around 300 kilometers per second to 700 kilometers per second, more and less. And just to give you an idea, with this type of velocities, it will take a couple of days, 4 days for 400 kilometers per second to reach 1 AU. And in this case, 1 AU is not exactly to reach the Earth, so I will mention that after. Solar flare. So what it is, it's a sudden increase of the solar electromagnetic emission, and during these type of events, a lot of radiation is emitted from the sun in different wavelengths, but what I'm most focused on is the particles that are emitted. So not only radiation can be emitted during these events, but also electrons, protons, and heavy ions, and that's what I'm more focusing about. And also the coronal mass ejection. So I don't know if you can see, but massive bursts of plasma. So plasma is emitted from the coronas, from the outer layers of the sun. And these type of events are usually associated with flares. So what we see is usually we first see a flare and then a CME, but it doesn't need to be that way. So we do not need to see a flare to after see a CME. It can only be just the CME. And here you can see the velocity. So CMEs can start around 200 kilometers per second, the velocity of the particles, which is more or less what we see in the solar wind. So these are the slower kind of events, but can go up to 300 kilometers per second. That's where I'm going to talk about more these kind of events. So much more faster, much more energetic, and much different from we normally see during the solar wind. During these kind of events, we can detect the solar energetic particles, the SCP. So energetic particles that are accelerated in either flares or CMEs, the two events that I've mentioned. The main difference is, at least in the timing, so in solar flares, we have impulsive SCP, so very short in time. This occurs during the magnetic reconfiguration of reconnecting of in the event. So energetic particles are emitted from the sun, but in a shorter period of time. So usually hours to a couple of days. During the CME, the particles are accelerated in the shock wave, and it produces a much more gradual event, at least in this timing analysis. So something that can start in a couple of days to a couple of weeks, it's possible to detect events with that kind of timing configuration. So two different type of SCPs depending on the sources. And one thing that I want to analyze when I'm analyzing the data that I detect with the spacecraft is which kind of source are we producing those particles. So this is just a first analysis that we can do, just the timing of the event. Okay, last the Earth radiation belt. So this is two belts of radiation that are around the Earth. The inner belt and the outer belt. The inner is more composed of protons, also some electrons, and the outer belt is mainly electrons. This is a very important radiation environment for this mission and for the instrument because it's a well-known environment. It's well-known, but it's also dynamic, so it can have an impact here in terms of dimension and in terms of flux. These belts are highly dynamic, especially the outer belt. It varies a lot with time, but even so, it's known. So it's a possibility to characterize and to calibrate the detector during the flight part of the mission. So it's the first time that we can calibrate and look to the detector's data during flight. So it's always an important radiation environment in that sense. So here you can see more or less how everything comes together in terms of fluxes and energy. So galactic cosmic rays, lower fluxes, but can go to very high energies. The radiation belts, also high fluxes, but more lower energies, and SCPs can have quite higher energies and high fluxes too. So how everything comes together, and this is the main sources that will impact the data of these detectors. Okay, so as I mentioned, the solar cycle, it's also important for this mission. So it has been discovered many years ago that the activity of the sun is not constant. It goes throughout a cycle of 11 years, and you can see here how it changes. This study is done based on the sunspots, so a number of spots that we can encounter in the sun, and this number of spots is related with the activity of the sun. And how does this impact on the analysis? So here you can see the data from EMP, a NASA mission, and on this top plot you see the data from a proton channel, protons around the hundreds of MeV to hundreds of MeV, so high energetic protons, and the number of sunspots in the sun. And you can see basically two different things. This dark line here is the background of this channel, so what the channel detects when there is no event happening, nothing from those SCPs that I've mentioned. And this line, it has an inverse proportionality to the number of sunspots. So higher number of sunspots, higher activity on the sun, lower galactic cosmic rays detected. But that's what's happening, because if the sun is more active, the magnetic field is also stronger, and it shields more the galactic cosmic rays, so we detect less. But it's the opposite thing with the events detected, the solar events detected during this period. So when the sun is more active, we have more solar events and higher fluxes from these solar events. You can compare here with the solar minimum, less events, and also the events that we have lower fluxes. So that's something that we have to take in consideration when looking to the data. So at least the background change a lot during the solar cycle, and it depends if we have emission during the solar maximum or the solar minimum. I didn't mention before, but this BepiColombo mission started more and less during this solar minimum and has been going throughout the evolution between the minimum and the maximum. Now we are during the solar maximum, so it's a good mission in that sense that we can cover this part of the cycle. So going to the minimum to a maximum. Now about the detectors. This is the detector that I've mentioned that I worked during my master thesis. It's BERM. It's actually a radiation monitor, so it's not part of the scientific payload of the mission. It is composed of 11 silicon stacks, and the main way of functioning, the particles enter the detector, deposit their energies throughout the silicon stacks, and by the energy pattern deposition in the detector, we can divide the particles that reach the detector in different channels, changing the species, so we can see if it's an electron, proton, or heavy ion, and we have a resolution of 5 or 8 channels in energy. So we will divide the particles even in electrons in 5 different channels, or in protons in 8 different channels. So this is a detector designed and built by FASEC, but after the mission was launched, it was the space rad group here on LEAP that started to look to the BERM data and to do the calibration and the characterization and all the analysis of the data after being launched. So this is what the channels look like for this detector. So this is the sensitivity of proton channels and electron channels in BERM. And what we can see here, it's, for example, for proton channels, we have more or less this box square function. So each channel is more sensitive to a specific range of energies, and it will always be little sensitive to higher energies. And this type of function, it's what we want in this kind of channel. So to say that the specific channel is sensitive to a specific range of energies and does not detect anything out of there. And after we have this shape, we will attribute an energy that can characterize each channel. So in the next plot, we will always see the name of the channel and an energy in this detector and in other detectors. And this is a specific energy that we have chosen that characterize each channel. And this made possible to compare data from different instruments. As you will see in the next slides, different instruments will have different response functions, so we have to find a way to compare both. As you see, in the electron functions, will have this so well-structured function because they are minima ionizing particles, so it's always a little bit difficult to have this type of shape that we want. Also, an important characteristics about this type of detectors, you will always have some kind of contamination. So these are the electron channels, sensitivity to protons, for example. You can see that they are still sensitive to protons, but less than they are sensitive to electrons, so that's what we want. But we have always to take in consideration during the analysis that electron channels may detect protons and vice versa, and when we can see those timings where the channels are detecting the other particles, so when they are contaminated, it's always important to highlight those and to take in consideration that don't use that part of the data. And I will show you in the future how this has to be taken in consideration. So here, another instrument from the same mission, this is SIXS, is part of the scientific payload, and it's very important to always take in consideration these two instruments. So when we do some kind of analysis, we use BERM and also SIXS. It's also an instrument that we use during the intercalibration of the instruments. So it's important to always keep comparing the data and try to use both instruments because they have similar technology also to do the analysis of the data. Just to show a little bit how SIXS works, it has a scintillator core in the middle, and then it has 5 different viewing directions, also with silicon detectors. So the main difference is that can detect particles from different direction, and BERM only has one direction. Here you can see, okay, the response function are different from SIXS and BERM. BERM is not so sensitive. It has less resolution in energy, but we want to try to do the maximum analysis possible with BERM, and for that we use also SIXS to have a more complete analysis of each event. Okay, here you can see one of the main advantages of BERM. BERM is a radiation monitor, but it's always on during the entire mission. So we have a good set of events. Everything here that you can see above this line is events that have been detected with BERM. And because it's always on, we have a great collection of events that we can analyze, can study, can compare with different instruments in the same spacecraft, in the same mission, and in other missions too. And here is the Earth flyby that I've mentioned before. But this continuous, the fact that it's continuous on and always taking data is one of the most important things of this detector. Okay. And here you can see the flyby that I've mentioned and why it's so important. So during the flyby, the spacecraft gets very close to the Earth and crosses very well the outer belt and a little bit of the inner belt too. And during this time, we can see how these belts are detected on BERM, as you can see here. On the top, the electron channels, and on the bottom, the proton channels. And we can... Okay, this is supposed to have regions, but okay, you can see. You can see the outer belt. The outer belt here and here. This is the inner belt, less detected by electrons. And in the proton channels here, very highlighted the inner belt where it's supposed to have more protons. Important thing is also to use this moment to characterize very well the detector. And as we already seen, electron channels can detect protons. And here is the first time that we characterize and we analyze to say how much these channels are being contaminated. In each case, these channels are being contaminated, and how can we avoid this and take this in consideration during the analysis. So that's why these moments are very important. And here you can already see that these are proton channels and they are detecting electrons. So this is the outer belt is not supposed to have protons here, at least with these fluxes, so we can establish that these are electrons and not protons. And an important thing also is that we can compare, during these moments, we can compare data from SIXS and BERM. So during this intercalibration, and the data is very good related BERM and SIXS, except here in these moments that SIXS has multiple point of view. So what we are seeing here is different directions. So in different directions, you can see different fluxes because they are pointing to different parts of the space. So talking about the different directions of SIXS, I will introduce here this concept of the pitch angle. So here on SIXS, you can see that has different point of views, and I'm not talking too much about the direction. I will talk about the pitch angle. So the pitch angle is the angle between the magnetic field and this midpoint of the viewing cone of the instrument. This will be more or less where the particles will on average come from this middle point. So this angle will characterize the angle between the particles and the magnetic field. So in that I'm going to use when I will talk about the different directions of this instrument. And in other instruments I will talk about the pitch angle. And here you can see during the Earth flyby how the pitch angles changes between SIXS and BERM. Okay, moving now to the analysis of one of the CME that I already explained what the CME is. And first, Conseguem ouvir? Agora dá? Ah, ok. Então eu posso usar isto. Tá? Ok. So, okay. Okay, I was just mentioning a little bit about this plot. So this is descent, solar radius. This is timing. So by the inclination, you can see how fast the particles are traveled. And here, these points are obtained with this type of plot. So here you can see the CME, and with different images in different timings, you can see how more or less how fast and slow the CME is traveling. So this event that I've been mentioning occurred 2022, and here you can see the data from SIXS. It's just an overview. So the electrons and protons, okay, here you see the background. It's a little bit higher than it should, also because of what's happening on this period. And this part is also important. It's just to highlight that it's not only BERM, but also other detectors have this. All detectors that work with this principle will have this contamination. So here it's very easy to see there is contamination, because you have, if it was not contamination, if this would be protons, you have lower energetic protons. So this is channels of lower energy, lower energetic protons reaching the detector before high energetic protons. So it would mean that the low energetic protons would be traveling faster than the high energetic ones. So this is the first hint that it's not that it's not protons. And you can see that the timing, the time structure match very well the electrons. So okay, these two first channels have electron contamination, and in this case we will not use this part of the event to analyze protons, at least. Okay, this is the spacecraft that I'm going to use, BEPI, Hertz, and Stereo. I think I already mentioned, because these are the ones that are more well connected with the event and the particles that are coming from the sun. These two are more close together. Stereo, we will see what we can see in this spacecraft that is not so well connected. So BERM and SIXS I already show you. Okay, no. Stereo, the other spacecraft that it's the other spacecraft that I've been mentioning, three different instruments that I'm going to use with three different energy ranges, and also some other characteristics like SEPT that have 4 viewing, like SIXS has 5, this one has 4. This LET is behind this, it has 16, and those are missions around the Earth, so orbiting the Earth, and also have different energy ranges, different viewings, like WIND have 8, ERNA has only 1, so okay, yes, this one I said. Then with this set, this very complete set of instruments, it's possible to look to the same event with different point of views in space and in different energy ranges, and do a good set of different types of analysis with different types of instruments. Here you can see the energy range that I'm going to talk about. So I will use data from electrons that will start more and less here on the, let's say, hundreds of eV to keV until to 10 MeV. And in protons, I will start more or less in the hundreds of keV to hundreds of MeV, so 3 orders of magnitude here for protons. And you can see also that's important to have a good set of instruments and of missions, because it will be possible to cover a higher range of energies. Okay, just now an overview of the proton channels. Here you see the 2 instruments that I've mentioned from BEPI, more or less the same thing. BERM is taking with less sensitivity the same event. But here you can see instruments on around the Earth. So two main differences between those type of plots. These ones are in a different position of space, so it might be detecting something, the same event, but in a different way. That's what you can see, the slightly different structure. And here you have lower energetic protons than in SOHO, so they are more or less in the same position, but different energies can travel and can interfere with the environment around differently. So that's why you see different structures for different energies and for these two type of instruments. These higher energies more and less match with what is happening in this detector that is also higher energies. So this is lower energies here on top. The electron channels, BEPI, wind that it's on around the Earth, and stereo, there is the spacecraft that is less connected with the event. It was the one more on the left in the other plot, and I will try to see what can be done with the data from stereo that it's not so well connected, and how can be related with the other sets of data throughout the different types of analysis that can be done during the event. So moving to what can we look when analyzing this type of events, there are mainly two different things that can be tried to analyze. So the sources of the event, and how does the particles propagate throughout the sun to the instrument, so how they interact with the environment around. And to do this kind of analysis, you have different ways of finding those parameters. The anisotropy analysis, so looking how does the flux changes with the direction of the spacecraft, of the channel. Velocity dispersion analysis, so here first in the anisotropy analysis, seeing how does the flux changes with the direction will also tell us how does the particle are traveling in the medium towards from the sun towards the spacecraft. So this is more about how the particles are traveling. Here in the velocity dispersion analysis, by the relation between the velocity of the particles and the time they arrive to the spacecraft, you can detect more or less how when the particles were emitted from the sun, so which kind of source can be related to, and we can also see the path, they calculate the path they have done throughout from the sun to the spacecraft, so get an idea of how they propagate in space. And also analyze the energy spectrum that will give us an idea of also how the particle interfere in the medium, and how does the energy spectrum changes from what is emitting from the sun, what we are receiving in the detector, and try to analyze that to have once again an idea of how they are traveling, and also what kind of sources can be producing this type of events. So first, starting with the anisotropy, what we use to study the anisotropy of event is this parameter called the first order anisotropy, and this relates with the cosine of the pitch angle that I've already mentioned before. So this is the normalized flux, and here you have the cosine of the pitch angle, and you can see that there are directions that have higher fluxes than others. And this is defined by the first order anisotropy. This is a parameter defined between -3 and 3. So -3 meaning that is more the higher fluxes around directions that have cosinus close to -1, and value closest to 3, which means that the cosine of the pitch angle is close to 1. This is not the only parameter, because as you can see, if this plot would be symmetric in relation to 0, this parameter would be 0. But even so, we have directions that have more fluxes than others, so it's not going to tell much about how the fluxes are being distributed from the different directions. So we could also have the second order anisotropy that will give a little bit more information about how the fluxes changes throughout the different directions, and with those two parameters try to analyze again how the fluxes changes throughout the different point of view in the direction in the instrument. And here we have a set of data from wind. Wind is a very good instrument to do this kind of analysis because, as you can see here, it has 8 different channels with different pitch angles, and this data it's pre-analyzed and it's put together in a way that each channel is more or less a constant pitch angle. And this is important because we always are covering the entire viewing direction. This is not the same for each instrument. So some instruments like SIXS have here pitch angles that changes throughout time, and it can be the case that in one specific moment all the directions are looking to the same pitch angle. So it's very important to have this type of instruments for this analysis. And you can see here that during this is the onset of the event, so this is a specific energy and different angles. Some directions have higher fluxes than others, so we can see that the particles are reaching the instrument preferential from one direction than the others. And how does it look in the anisotropy analysis? We have here a peak towards the minus sign, so this will tell us which direction are receiving more particles than the others. And at least during the onset, this is a typical moment during the event when should be something in the anisotropy. So it's when the particles are reaching the instrument. At least at that moment, it should be from a specific direction. Then throughout the rest of the event, we might have some structures that can relate to how does the particle are traveling and how does the particle are interfering with the medium between the sun and the spacecraft. So that's what we are seeing here. Moments in time when the fluxes can be the same throughout so the event can be isotropic or anisotropic throughout different moments in the event. And here you can see how it looks for these are different energies, the anisotropy in different energies. You cannot see here for protons and electrons. So once again, this peak related with the onset that you can see here for higher energies and here for lower energies. And then you can see that throughout the rest of the event, we can still have some anisotropy structures that will change or not with energy, and that will tell us a little bit about how the event, the particles propagate. So in the velocity dispersion analysis, one of the ideas is to find the onset of the event, and here you have a plot quite similar with the one that I presented before. So in this case, instead of distance in one axis, we have the inverse velocity and timing on the others. And here you have the time of the 3 flares that I've mentioned before. And you can see here the data from a specific set of data. In this case, it's from winds. And these dots are the onset of the event in each and specific channel. So the inverse velocity relates with the energy. So each specific point relates to an energetic channel, and you can see that have different timings of arrival to the instrument, and we can relate those points to try to infer the injection time of the event and also the distance that the particles have traveled to reach the spacecraft. So in the other plots, the inclination would indicate the velocity. In this plot, we have the velocity in the axis, so the inclination indicates the distance. And as you can see, the distance will always be higher than 1. That's what we're expecting. Yes, and we can find these 2 parameters based on this analysis. One important thing, this way of finding the onset of the event, it's quite a sensitive analysis. That's what I'm trying to show you here. So this is a method to analyze the onset of the event. Here you have some data from SOHO, and this is a method very used to obtain the onset. So this method relies on, okay, once again, you cannot see the background, so this area here should be the background. It's highlighted. So this method relies on the background, so analyzes the background, and the idea is try to give a signal. In this case, the signal is the onset when the data gets away from the background. It's different from the background. And in that way, we see that we have an onset. So we are not at this moment, we are not in the background regime. So that's what the method does. One important thing, and the main problem of this method is it relies a lot on the background. So we should have well-behaved background. But as I mentioned before, at least during the solar maximum, there are a lot of things happening at the same time. So this background, it's not what we see in different channels. So for this plot, I've chose a channel with more or less high energy. So this is higher than the rest of the plots I'm going to show you. And you can see, okay, for higher energies, the background can be more or less constant and well behaved. And we will find very well the onset of the event. But okay, this is a much lower energy channel for wind, and you can see two different things. So first we have here the what I call the instrument background, and here an event background, so something else that was happening before this event I want to study. And if I use this method, so if I chose here a background, this will always give me an onset that is clearly after the onset that I'm looking for. So I should try to find different methods of finding the onset, at least that can cover this type of problems. And in this one, it's a much simple one where I've tried to find the maximum flux of the event and try to see, look to the onset based on the percentage of this maximum. So it should be a low percentage, obviously. And in this case, we can have more or less a good method to find or a constant method to find the onset throughout all the channels, independently if they are higher or lower energetic channels. But even so, if the background it's high, this will have some problems too. So the last method I'm going to show you here, and the idea is to try to use these three methods depending on the event and depending on the spacecraft and the data that we have. So in this case, I'm fitting the moments before after the onset, and trying to find when this fit meets the background. This analysis it's a little bit more powerful in this sense, because this point when it meets the background, it doesn't need to be what I called the instrument. It doesn't need to be the background right before the event. So I can fit this part of the data and try to see when it meets this background line here instead of that one. So different methods will give different ways of trying to find the onset depending on the data and on the instrument itself. So the last one, the energy spectrum. So we have a power law coming out from the sun. So the particles will follow a power law, but this is not what we detect. So what we detect can be either power law times an exponential, or in some cases something closer to a double power law that has been mentioned, that could indicate that we have different spectrums of power law times exponential, and this double power law in this case would be a combination of different spectrums that we are seeing together in the instrument. So trying to analyze which kind of spectrum do we have, we can try to see how the particles, so which kind of event could be emitting those particles and how they are traveling. Here, try to understand which kind of spectrum can we best fit to the data, and try to take the maximum information about the way the particles travel from the sun to the instrument based on that. And okay, here you can see an example. So the colors match the colors here on the plot. So the yellows mean that it's on BEPI. The green it's on Earth. So here you have sorts of different types of fitting. So only with one spacecraft or multiple spacecrafts, And the idea here is try to find the parameters that best fits the spectrum that we have. So this is multiple instruments in the same spacecraft, and try to see if the spectrum stays throughout the entire energy ranges, of if you can have different spectrums depending on the energy. So this type of analysis can be very helpful to understand how does the particle are traveling and what is happening in different energy ranges. So it might not be the same for every for the entire range. So this is just a method that I'm not presenting you here. Is something that I'm still working on. So it's the 1D propagation model. This will be very helpful to get some other parameters from the event, because you can fit a model to the data, and this model relies on three free parameters. One is the mean free path, so it will give an idea of how the particles are traveling, and the other two parameters are related with time. So in this case, with the injection profile of the event, so it will give an idea of the source and how is the source behaving in this event. If in this case, if it's a very short period of injection or something more broad in time. So this is also very helpful to try to understand different sources and different ways of propagating. And okay, this just to mention that this changes with the velocity. So it's also important to have in consideration what was the medium before the event happened. So this enter in this model throughout the particle velocity before the emission, and also here the energy of the particles that we are studying. Okay, and comes to the conclusion. So planetary missions can be also important to study heliophysics. That's important. So in this case, I'm showing you a mission that it's a planetary mission, but I'm using the data more to focus on what's happening on the sun. Diverse missions and instruments will also give a more complex way of studying the event. And just mention that it's also very important to first look to the instrument instead of first look to the data, because it's also very important to know what the instrument is doing and to take care when analyzing the data, so based on the instrument. And it's the end.